Okay, well, thank you for showing up in this sort of holiday week. It's sandwich between two holidays, Monday and Friday. So we'll be at least presumably holiday after this lecture, unless we have something else later on this afternoon after the lecture. So what we're going to do today is, in the last few lectures, we've been up in the stratosphere, as it were, of large sets and large cardinals, looking at cardinal arithmetic, firstly of large sets, and then last week properties like being an inaccessible cardinal and the existence of growth in the universe, and these kind of properties that involve the existence of very large sets. So today we're going to really come back down to Earth, and for the next 2 weeks, and our main focus is going to be, for the next 2 weeks, our focus is going to be on subsets of the real numbers and similar structure. I'll say in a moment what I mean by similar structures. So if you first see we're looking at subsets of the real numbers, you might think, well, there's not much that can be said about subsets of the real numbers. But of course, if you just think about the continuum hypothesis is to do with subsets of the real numbers. It says that the hypothesis is that every infinite subset is either in bijection with the either countable or has the cardinality of the real numbers. So we know that subsets of the real numbers, that there are tricky questions to address about subsets of the real numbers. There's actually a principle from which the continuum hypothesis follows that's a perhaps plausible principle about the real numbers, and this is called the perfect set property. And this says that every uncountable subset of the real numbers contains a perfect subset. Hands up if you know what a perfect subset is. Right, nobody, that's fine. That's the main thing we're going to do today. On the other hand, I mean, you would have done it in Slovene, and I guess it's I don't know. Would that be? But I'm not sure what the Slovene is. But you might have potentially done it in a course on topology. Anyway, we'll see what a perfect subset is very soon. The point about this property is that one can prove that perfect sets have cardinality to continuum. So if we have the perfect set property, the continuum hypothesis cannot be false, because if we have an uncountable subset of the reals, then it contains the perfect subset, and that perfect subset has cardinality of the continuum, so therefore the whole set also has cardinality of the continuum. Okay, so this is the perfect set property as a fully general property about the power set of real numbers, the perfect subset of the real numbers. But this property is consistent, but in a subtle way, in the same way that in the same way that the existence of a large an inaccessible cardinal is consistent. I'm going to address consistency properties properly, consistency of properties properly in the last lecture of the course, so I don't want to talk too much about consistency now. So in today's lecture, what we're going to do is, we're not going to assume this is an axiom. We're not even really going to get to this. We're going to use the perfect set property. We're going to use the tool of perfect subsets as a way of investigating sets of real numbers. And we're going to prove that for certain kinds of sets of real numbers, certain kinds of sets of real numbers do enjoy this perfect set property. And so such nice kinds of sets of real numbers cannot contradict the continuum hypothesis. And in a sense, one reason for looking at this is if one goes through nice classes of sets of the real numbers, and one shows that nice classes of sets cannot violate the continuum hypothesis, it's a way of establishing that the continuum hypothesis is sort of natural on the one hand. Whether or not it holds as a general property, that's still a question. But if it doesn't hold, counterexamples to it cannot be of the nice kinds of sets that we're going to look at. We're going to look at families of nice sets and establish this perfect subset property, or them showing that such families of sets cannot violate the continuum hypothesis. And because this is, so although we're not going to tackle exactly this property generally, because perfect sets are important, the title of the lecture is the perfect set property. And we're going to really look at it for subsets of the real numbers. But one thing that's important is that what we're going to do today applies to more general classes of structures, not just the real numbers. And although I'll focus on the real numbers, because it's what everyone's more accustomed to, and everyone's probably comfortable with the real numbers, well, hopefully comfortable with the real numbers, I still want to say what the right generality for what we're going to do today is. So, today we'll focus on the real numbers, but the proper level of generality is something called Polish spaces. As in spaces from Poland. Hands up if you've heard of a Polish space. Oh, yes, okay, well, surprising. I was expecting nobody to have heard of a Polish space. Can anyone define what a Polish space is? You've heard of it, So the Polish space is a topological space defined by a metric, but not just a metric, it's a complete metric, so it's the topology of a complete metric space. And moreover, that metric space needs to be separable, which means that it has a countable dense subset. They're defined by a complete separable metric. It's the metric topology defined, and I say via as the metric topology of a complete separable metric. So the complete means every Cauchy sequence has a limit. Separable means there is a countable dense subset. But as I say, I just want to say this is the right level of generality. I'm going to state results at this level of generality, but the proofs, in order to make them more comfortable, I'm going to just work with the real numbers. Just to say, so examples of Polish spaces. So one is the the real numbers with the standard Euclidean topology on it. Of course, that's defined via a metric. Of course, it's complete because every Cauchy sequence in the reals has a limit. And it's separable because there exists a countable dense subset. So what's an example of a countable dense subset of the real numbers? Sorry? The integers aren't dense. Yes, but the rationals are dense. Okay, so that's the example we're going to work with. I want to just mention one other example of a Polish space, because this example is going to be very important next week. And I want to mention it now so you've got time between this week and next week to think about it for yourself. So this is the space of total functions from the natural numbers to the natural numbers with the metric. So d, the distance from, let's use f and g for functions, between two functions is, well, it's obviously, so in the case that the functions are the same, what does the metric need to be? It is 0. Okay, that's dictated by a metric space. And in the case that they're not the same, it has to be non-zero, it has to be positive. Now we've got functions from the natural numbers to the natural numbers. You simply look at the least argument, the least number as an argument on which they differ. And a standard way of defining the metric is taking 1 over 2 to the power of that number. You can also take 1 over the number. I mean, there are many ways of doing it, but I like doing it this way. So 1 over 2 to the n, 2 to the little n, where n is the smallest number such that f of n is not equal to g of n. So this is if f is not equal to g. So one way of viewing the elements of this space is as infinite sequences of natural numbers. And you've got two infinite sequences that disagree somewhere, you count along until they differ, and then you look at the index of that. So 0 is the index of the first place, and 1 the second place, and so on. And you take 1 over 2 to the end as that as the distance between them. So as an exercise between this week and next week, verify that this is a complete separable metric space, and try to think about what the open and closed sets in this space look like. Okay, but most of what we're going to do is going to be about the subset today, about sets of real numbers. And I want to look at subsets of the real numbers with an eye to trying to answer the continuum hypothesis restricted to special subsets. So showing that as we look at sort of well-behaved subsets, we can't violate the continuum hypothesis. And we're going to get nice subsets, we're going to start off with topologically nice subsets. So let's start off with open sets of real numbers. And the question, for which the answer will always be no, is can we violate the continuum hypothesis with an open set? Well, in this case, with an open set, but as we go into other classes of sets, can we violate the continuum hypothesis with such and such well-behaved kind of set of real numbers? The answer will always be no, but the reason for that might be some. But let's start with open subsets. So open subsets of the reals. And the question is, what are the possible cardinalities? For an open subset. So, what cardinalities can an open subset of reals take? 0, right? Because we got the empty set. Very good. What else? In the quiz last week, also omega 2, but today we're working with the axioms of set theory. So we're not going to assume that 2 to the aleph 0 equals omega equals aleph 2, right? Like in that assumption is just for the quiz. And moreover, today we're going to just assume dependent choice instead of it. We don't need the axiom of choice today because we're dealing with like low-level sets. Well, we will need it at one point later, but I'll tell you when we need it. Okay, so what's the other possibility for the cardinality of that? Yeah, 2 to the aleph 0. So just the continuum. And those are the only possibilities, because any non-empty open set is a disjoint union of countably many open intervals. Okay, and every open interval is in bijection with the whole real set. Okay, so that's very easy. So what about closed subsets of R? So again, what are the possible cardinalities? Question mark. So it's the same question. Finite. Okay, any finite cardinality. Again, we have the empty set, but if we take the integers at 0 up to n-1, that's a closed set. So any finite number. Okay, what else? Aleph 0. So what would be an example of a closed subset of aleph 0? Yeah, the natural numbers. So for aleph 0. Anything else? 2 to the aleph 0. Now, if we basically, if the continuum hypothesis is true, that's everything we can have. But what we're going to actually spend rather seems a very simple property, but we're going to spend rather a ridiculous amount of time proving is that in fact we can prove that these are the only options. So we can prove from the axioms of set theory that every closed set has one of these cardinalities. That is, we can prove that any violation of the continuum hypothesis cannot be a closed set. So it might seem like a tiny thing, but if you want to think for yourself about whether you can find an easier argument, then it's going to take us quite a bit of work to prove it. So let's put it as theorem. From the axioms of set theory, dependent choice rather than the full axiom of choice, we can prove the only possible cardinalities of closed sets are indeed finite, aleph 0, and 2 to the aleph. This closed sets general closed subsets. Aha. Yeah, sorry. This closed subset of the real. But actually, it's more general because it's also closed subsets of a Polish space. But it's not true if you start talking about other very strange topological spaces. So Vasilia?
I want to ask about competition.
Aha, yeah, so that's the. But in fact, this theorem we're going to get as a result of 2 theorems. So I'm going to state what the 2 theorems are. And I'm actually going to state these theorems in the context of Polish spaces because that's where that's the natural that's the natural framework for these theorems. But I'm going to prove them in the real, for the set of real numbers. So just to say that this focus on Polish spaces and okay, well, no, we'll leave that. But the theorem follows, this is the theorem I'm motivating, but it follows from two theorems. The theorem on the other board follows from two theorems. So let's call them, it'll be good to number them the same as in the notes. So I think I'll call them theorem. I think I call them theorem 1 and theorem 2. Okay, now this is theorem 1. So theorem 1 follows from two theorems. So theorem 2 is that in any Polish space X, the collection of closed sets enjoys the perfect set property, where, well, when I first stated the perfect set property, I was talking about the perfect set property for all sets of real numbers, all subsets of real numbers. And now I'm talking about the collection of closed sets enjoys the perfect set property, which is every uncountable closed set assume as a perfect subset. So that's theorem 1. Basically, it's just saying if we're in a Polish space, that any uncountable closed set has a perfect subset. But I've packaged it like this in order to again talk about the perfect set property. Because in general, the perfect set property is a property that we can talk about for a collection of sets. And as a property of a collection of the sets, it says if we have an uncountable set in the collection, then it has a perfect subset. I still haven't told you what the perfect subset is, but we'll come to it. In theorem 3 is that in a Polish space X, every perfect set has cardinality due to the Ellis-Diff. Okay, and it's just trivial that these two in combination give us. Okay. So what do we mean by a perfect set? No. A perfect set, or a perfect subset, if you like, but a perfect set in a Polish space X. But if you don't like thinking about Polish spaces, whenever I say Polish space, just think about the real numbers. And bear in mind that for next week, you need to also think about for next week, you'll need to think about the space of total functions from natural numbers to natural numbers, which I should have mentioned is also known as Baire space. That space is an important topological space. and it's homeomorphic to the subspace of irrational numbers in the real number. Maybe you should have mentioned that at the time. Irrational. So a perfect set in a Polish space is a subset. This is the definition of perfect set. Is a subset Y that is enjoys three properties: non-empty, closed, and the last really important property, that every point in the set is an accumulation point. Every point in Y is an accumulation of points in Y. Right, so non-empty, you know what it means. Closed, I hope you know what it means. If you have a Cauchy sequence of elements, I mean, in the case of a metric space, as we're in, if you have a Cauchy sequence of elements in the subset, then its limit is also in the subset. An accumulation point is an element Y in Y is an accumulation point. Here. So accumulation point means it's a limit, it can be obtained as a limit of other points in this, from other points in the set. So in other words, that's equivalent to saying for any epsilon ball, however small, we put around Y, there'll be some point in the set Y that's different. There'll be some point in the set Y different from little y that is within the form. So if for every epsilon greater than 0, there exists a y prime in Y such that y prime, well, is not equal to Y, but we can just say that by the distance from y prime and Y is less than epsilon. And greater than 0, which means they're not the same. Okay. And there's also so this is an accumulation point. There's a negated version of the notion of accumulation point. Does anyone know what that's called? If a point's not an accumulation point, there's a word for that. Isolate. Very good. So an element Y is isolated. So if it's not an accumulation point, but equivalently, so if there exists an epsilon such that Y intercept the open ball. This is the open ball centered at little y around the point, but centered at little y. This is just the single to the y. But it's the same as saying it's not an accumulation point. So another way of saying, and I'm going to change the definition, another way of saying that the set is perfect, if it's non-empty, it's closed, and it has no isolated points. Okay. So have you met this notion before in topology courses? Right? There's some. So let's look at the real numbers and find some examples of perfect sets. So perfect sets in reals. So can anyone give me an example of a perfect set so actually, an example of a perfect set in the real? So the easiest example is the whole of the real. Very good. Or any closed interval. Any closed interval if A is less than B. Okay. And then there's another style of perfect sets. Sorry? Also unions. Yeah. So also a finite union of closed intervals, but not in general an infinite union. Yeah. So good. But there's another very typical example, as we'll see, of a perfect set that's very famous in the real numbers. It has a name, the cantor set. So, I was talking about how the heroes through this course keep on changing, but cantor keeps on coming back, and cantor's coming back now. Again, so cantor is going to be a big hero for today. We're going back to 19th century mathematics. So there's the very famous cantor set of real numbers, which you might see that in many guises. So it's one often meets it as an example of a subset of the reals that has cardinality, the continuum, that nonetheless has measure 0. That's one of the ways that it often arises. So let's remind you what the cantor set is. So you can put it in different places, but I'm going to do it between 0 and 1. So we're going to start off with the closed interval 0, 1. And this I'm going to call K0. And the idea of the cantor set is we approximate from above. We're going to get the cantor set as an intersection by performing the procedure that at every step, we look at the collection of intervals we've currently got, and we throw out the middle third of that interval. And we throw out an open interval, so we're left with closed intervals. So K1 will be, I'm going to throw out the middle third, so it's about a third of the way. Yeah. Maybe I should be writing on the right, but this is let's just put equals. Now this is 0, 1/3 union 2/3 1. And so K2, we've got 2 intervals to throw the thirds out, the middle third out of, so we get something like this. Well, and anyway, in the notes I go a little bit further, but I think you can imagine how this continues. I mean, in the end, define K infinity to be the intersection over the index by the natural numbers of K sub f. So notice at every point we've got a closed bounded set. And they're shrinking. So this is a decreasing intersection because the sets are getting smaller. Intersection of at each stage, they're closed bounded sets. So what is the quality that closed and bounded sets in the real numbers have? A closed bounded set is a is a compact set. It's the same thing as a compact set. So it's a decreasing intersection of non-empty compact sets. Hence, by some general topology that I won't go into today, its intersection is also a non-empty compact set. Hence closed. So we've seen that the intersection is non-empty and closed. We just need to show that it doesn't have any accumulation points. So in other words, that all its points are accumulation points. In other words, it doesn't have any isolated points.
Is this also true for Polish that is computation for compaction?
Aha. Well, so I'm only talking about a particular cantor set in the reals. It is actually true in the Polish space that a decreasing intersection of non-empty compact sets is a non-empty compact set. However, the analogues of the cantor space are not actually necessarily compact in an arbitrary Polish space. But actually, all one really needs here is closed and sufficiently bounded by distance that you can prove that the intersection is not empty. So the general spirit of this goes through in the general spirit of this. But then, I'm talking about a particular section. I'm using what's necessary. With something later, I'll say that it needs a bit of modification when one deals with the Polish space. But I want to focus on the reals today. So I want to prove that it doesn't have any isolated points, but at the same time, another thing I want to show is, which is related to theorem 2, but this is of course an example. We're not proving a theorem here, but I want to show that this set has cardinality, the continuum. So let's do that first, and then when we've done that, we'll have a better handle on what the points of it look like, and we can see that there are no isolated points. So the cantor space, where we have the cantor set. So it's the intersection over the natural numbers of these k's. And each kn can be viewed as, we can view this as, so what, let me see what I use in my notes. So I'm going to give names to these intervals. And the point is we have a tree going down here where we have the root here. We have two branches going down. And then this divides again, we have two branches going down. So we can naturally name these intervals using finite words over bits. So over 0, 1. So this interval, which I'll call D, I don't know why, but just to be consistent with the notes, I'm going to index by the empty word, which is a kind of curly epsilon symbol for the empty word. Here we have D0, and here we have D1. So I'm just using the words to tell me which way to go as I branch down the tree. So here we have D00, D01, D10, and D11. And then we can see that each kn is the union over words of length n of the d of those words. So this is, let me just put the full thing here, but this is the intersection over the kns, and this is the same as the intersection of over the ends of the union of words in So I'm going to use the computer science notation 0, 1 star with a set of words over bits, where the word length is n of the d sub x. Okay. And now we've got an intersection over a union, and in set theory, intersections and unions distribute. And what everybody knows that like the finite distributivity law, but there's also an infinitary distributivity law called complete distributivity for intersections and unions. And I'm just going to use it here. And if you want to, you can think about it for yourselves to justify its validity. But an intersection over the unions is the same as a union over all functions from the indexing set here to the indexing set here. That to the indexing set here that depends on the indexing set here. So in our case, this is equivalent to unioning over all f from the natural numbers to 0, 1 of then the intersection as we go along over the natural numbers of d of f of f. So what this is saying is it's saying the intersection of these horizontal rows here. It's easier to see it pictorially. The intersection of these horizontal rows is the same as the union along all infinite branches. So think of all infinite branches through the tree of, for each branch, we take the intersection of the intervals that goes down that branch. Okay, so here we're unioning over all infinite branches through the tree. The intersection as we go along the branch of the intervals here in the branch. But along each branch, the intersection we've got is again an intersection of non-empty compact sets. So it's again non-empty. Moreover, because the width of the set here is 1, then a third, then a ninth, then 27th, and then it goes down in powers of 3, the width of the closed set, we necessarily get as an intersection of closed sets at the bottom, is necessarily 0, so it's a singleton. Okay, so this is, we can see that these are all disjoint. This is then a countable, not a countable, this is the disjoint union of singletons. And hence, cardinality of this set is, well, we've got a disjoint union of singletons indexed by a set of cardinality 2 to the other 0. So the cardinality of K infinity, so hence the cardinality of K infinity is 2 to the other 0. How are we doing for time? Okay, and now we want to see that there are no isolated points. So let me call this little k sub f. Okay, for the element in here. We want to prove that there are no isolated points. No k sub f is isolated. Well, consider k sub f. And consider any f. So we want to prove it's an accumulation point. Consider any epsilon greater than 0. Then because the widths here go down, so 1, a third, a ninth, a 27th, we just let n be such that 1 over 3 to the power of n is less than epsilon, then if we consider any other f prime that agrees with f on the first n element on indices 0 up to n minus 1, k sub f prime is going to be k sub f prime also will be within that distance because it lies in the same interval here. So yeah, so let's just write it down. Then any f prime with f prime n equals f of n for all n less than equal to n enjoys that the distance, well, so we're just talking about the distance in the reals, so the distance between kf and kf prime is less than equal to 1 over 3 to the n. So indeed, it doesn't have any isolated point. There's a nice way of thinking about the cantor set as well, which is you can represent. So here we've got this is 0 and this is 1. I should have said that. Well, I did here. This is 0 and this is 1. So you can represent numbers between 0 and 1 in binary representation as infinite sequences of bits after a binary point rather than a decimal point. By the same way, you can represent them in ternary notation, so base 3 notation as infinite sequences of 0s, 1s, and 2s. And the cantor set is exactly those numbers that have a representation in ternary notation using only the digits 0 and 2. So that's a nice way of thinking. Right, so it's 3 o'clock, so we'll have a 15-minute break and start again. And I'm happy to take questions, but I'm going to go for my. Okay, as I pointed out during the break, I made a mistake in this formula here for the distributivity. So the best way to see the distributivity is here we're looking at the intersection over the depths in the approximation of the unions of intervals that lie on each depth. So here we're intersecting each of these unions of intervals. And one can view that as a union over paths, as I said, of then the intersections of the intervals. So path with the tree of the intersections of the intervals that lie on the path. So there, the paths are given by functions from the natural numbers to 0, 1, but then I was incorrectly labeling the intervals that lie on the path because the intervals are indexed by words, and the correct word here is to use the f, the function. It's giving us infinitely many bits, and we want the first n bits from the word of the first n bits from that as the index. The other way of viewing this formula as arising is, and so I don't have time to pause on this in the lecture now, but this is the general distributivity law between unions, infinite unions and intersections that's valid for set theoretic unions and intersections. You can think about that. It'll be on the video and you can think about that in your own time. Now, having looked at the cantor set, what we've seen is the cantor set is perfect and that it has cardinality 2 to the Alex 0. And this leads us naturally to theorem 3, as we stated it. So theorem 3 was that maybe I'll run off this part of the board, so that formula is still around for a while. So theorem 3 was that in a Polish space, any uncountable closed set, any perfect set has cardinality the continuum. I'm going to prove it just for this special case of the real numbers. So let's state it again for the real numbers. So theorem 3 in the case of real numbers. So every closed every perfect subset of the real numbers has cardinality 2 to the n of 0. And the main idea here is that when we have a perfect set, we can find something that looks like a copy of the cantor set within it. It won't be exactly spaced in the same way as the cantor set, so it's not that you're necessarily in the interval from 0 to 1 and you're necessarily cutting out 1/3 each time, but nonetheless you're in some interval and you're cutting something out of the middle each time. And there will be a copy, and you know, it's in that sense it looks like the cantor space. So the cantor set. In fact, topologically, it will be a compact, or it will contain within it, if you have a subset that is a compact, totally disconnected subset of the original stuff. But we don't need to worry about that. So in order to do this, there's a lemma. And this is a little bit fiddly. I need to remind myself. So the lemma says, if we have a subset of the reals that's perfect, and there exists an x in A bounded by A with some number little a below. There's an x in the perfect set bounded by little a below. Then at least one of the two sets, and at least one of the two sets, I read right at least, below that. And the two sets are either A intersected with the closed infinite interval from little a onwards, or A intersected with the open. The point here is that we're cutting down our perfect set A, we're bounding it below by little a. We might be bounding it below such that it's a strict, little a is a strict bound in this case, or we might be bounding it below such that little a is a non-strict. But little a is actually part of that. So we use this case if little a actually lies in the set A and is an accumulation point of points in that from, I mean, A is perfect, so it needs to be an accumulation point, but it's actually an accumulation point from points that lie to the right. In that case, we need to include little a in this set. If little a is in the set, but is only an accumulation point from points to the left, we need to use this one, because we can't put little a in. If we can't bound below by little a and include little a in the set, because we've lost all the points that are possible. If little a is not in the set, then we can use either. Okay. And there's a dual lemma which says exactly what you would expect for if x is bounded above by some b. Then you can also cut the set A off if the set A contains an element that's bounded above by some B, then you can cut the set A at upper bound B, either by including B, not including it, or retaining the property of B. Okay. The proof of this is straightforward, a little bit tedious, and it's not worth doing in a lecture, but it's something to have fun verifying yourselves. And if you don't do it before next Wednesday, you can probably do it in the exercise class next week. So once we've got the lemma, we can now prove theorem 3. Let's use this. Basically, we're going to do this by, as I said, constructing something that looks very much like the cantor set. So proof of theorem 3 in the case of the real numbers. Okay, so we want to show that the cardinality of A is greater than or equal to, well, is 2 to the aleph 0, and it's obviously enough to show that it's greater than or equal to 2 to the aleph 0. But basically, we're going to, I've rubbed the picture off now, but bear in mind the picture we had of these intervals of approximating the cantor set as unions of intervals at each level and refining them to unions of a larger number of intervals. So at each level we go, each further level we go down, and we were indexing those intervals by words that gave us paths through the tree. So I'm not going to draw the same picture again because we had it there before, but we're going to use the same notation. So we construct a family of bounded perfect subsets of A, which I'm going to call A sub W, where W ranges over words in over 0, 1. Again, each AW is replacing the DW we had before. So each of these is going to be like one of the intervals we had, one of the particular intervals we had in tree of intervals that gave us the cantor set. So we need to start with at the root of the tree, so that's with the empty word. And we let A, the empty word. We can't start with, we might not be able to start with A itself, because A might not be bound. We want these to all be bound instead. But how can we bound A? Well, we use lemma. We use the lemma. A is inhabited, so there exists some point in it. We use this lemma. We take some lower bound, and we use this lemma to bound it below, and we use the dual of this lemma to equally bound it above. Okay. So it equals some bounded subset of A aimed using that. Okay, and then we're interested in how we define A of W for a non-empty word. Well, suppose we already have AW and some word W. We're going to say what we do to partition this word. So this is like an interval, like the DW we had in the construction of the cantor set. And for each DW interval, we partitioned it by throwing out the middle third. So we're going to do something similar here. So how are we going to do this? Well, AW is a bounded perfect set. So it's a bounded closed set, so it's compact. So it has a maximum and a minimum element that it contains. So we let A be the minimum element of AW, and we let B be the maximum element of AW. And actually, we do actually do something like throwing out the middle third. So we simply define AW followed by 0 to be, we take the interval A, we're going to go a third of the way from A to B. So that's like 2/3 A plus 1/3 B. Intersection A, AW. If this is perfect, and otherwise, if it's not perfect, we take the open interval here at the end. Otherwise. And this lemma guarantees, this lemma together with, well, in this case, it's actually the dual case for the upper bound. But this lemma for the dual case guarantees that this is that one of these two is perfect. And we do exactly the same thing for well, not exactly the same thing, but we take the right-hand third of the interval between A and B for the one branch, for taking the right branch. So this is either 2/3, sorry, 1/3 A plus 2/3 B. We can always include the A here and the B here because we know that A in this case, well, A and B are both elements of the perfect set AW. So this is perfect. And otherwise, we now put an open, we make the half interval open at this, make it the half open interval of this thing. Use the B intersection AW unless. Okay, so yeah, one of these is perfect, one of these two options, and one of these two options. So we always get a division. It looks like we're always throwing out the middle third, but because when we do this, we intersect with AW, we don't necessarily go all the way to the endpoint. AW, we don't exactly know where AW is inhabited in the middle. We actually end up getting the intervals don't go down, even though it looks like we're taking them down by a factor of 3 every time. They don't actually literally go down by a factor of 3. They can go down faster than that. But nonetheless, the construction works, and we, of course, define A infinity we define A infinity to be the intersection over natural numbers of, for each natural number, the union over words of length n of the AWs. It's exactly the same picture before, intersecting the unions of what were intervals before, but now all we know, these aren't actually intervals, but we know that each one's a bounded perfect set, and we know we've got constraints on the upper and lower bounds of the set. And because, yeah,
A scientific question. Meant to ask with for the children, right medium of A omega.
aha,
We have the nice notation.
I don't want to call that a stupid question at all. It's a good question. Let me come back. Let me finish the proof, and then we'll come back to that. That's a nice way of relaxing at the end of the proof. I mean, we're very very much at the end of the proof in any case, because I'm going to cheat now. I'm not going to cheat, but I'm going to avoid the details, because the rest of the details are just the same as what we did in the cantor, for the cantor set. So each, we've got for each n, we've got bounded. This is always a bounded closed set, hence a compact set. So again, we're intersecting. It's an intersection of a decreasing sequence of non-empty compact sets. Hence, it's non-empty. But moreover, the same distributivity law gives it as a union over the infinite branches of intersections. And again, exactly the same argument as before gives us that those intersections are singletons. And then it's got cardinality to continuum by the same argument as before. So basically, by the same arguments, I don't want to repeat them, but it's literally the same argument as for the cantor set. The cardinality of A infinity is 2 pi 0. And that's enough detail there. So now you've got your next question. Why use infinity when we could use omega for infinity as a notation? So in fact, I came to revise my notes yesterday from notes for previous years. And in previous years, I used omega rather than infinity. What I didn't like is using omega in this case because we're using W per word. But there's the potential confusion between omega and W with my bad writing. And in a sense, we're not going further up the ordinals. If we're going further up the ordinals, then of course we would use omega because we would be carrying on. But in this case, it's like just a mathematical construction in which we've done countably many things and then we have an end result. And it's quite common to use infinity in such things. But anyway, until yesterday, the notes did actually have omega in this condition. But I remember in previous years trying to write out arguments having omegas and W's and then getting confused. I mean, maybe just me, not the students. But, anyway, so that is theorem 3. So now we come to theorem 2. And theorem 2 is where cantor was a real hero. So this is a beautiful argument. So theorem 2, none of you have seen this kind of stuff in this college before. I mean, because sometimes people do this sort of thing.
We did some cantor set, for example. I think we explicitly talked about this before.
Yeah, I mean, yeah, but not the Polish spaces. But
yeah.
So for example, the next thing, the next result. So theorem 2, again, we're going to do it for special cases of the reals. There is one other remark to make about this. But I say the same argument is for the cantor set. So actually, in the case of the Polish space, there is actually a little change one needs to make in the argument, which is in the case of a general Polish space, it's not necessarily the case that these bounded these bounded perfect sets are compact. Okay? And in that case, you can't use the argument that the intersection of decreasing sequence of non-empty compact sets is non-empty. But what works here is that if you have an intersection of decreasing closed sets, non-empty closed sets, and these closed sets have diameter bounded by a decreasing sequence that converges to 0, then the intersection is still not. So there's that little modification in the case of Polish. Right. So theorem 2 is now, we know that our perfect sets have cardinality for continuum. The theorem 2 is to show that the perfect subset property, every closed set contains a perfect subset. Every closed set, A, real numbers, because we're doing it in a real case, contains a perfect. Okay. The proof. So we've got to close every non-empty, uncountable closed set A. Did I have this? Did I have uncountable in theorem 2 when I stated it the first time? I hope I did.
No.
Okay, well, that was a bad omission.
You said it.
Well, anyway, it needs to be. I mean, the integers are closed in the reals, and they clearly don't have a perfect subset because perfect subsets have cardinality continuum. So sorry about that. Every uncountable closed set contains a perfect subset. I suppose. Okay, but then the perfect subset property is that if a set is uncountable, then it has Yes. Okay, so I did mention uncountability there, at least, yeah. Anyway, good. So now we're going to have it in this form. Every uncountable closed set contains a perfect subset. So suppose we have an uncountable closed set that's not perfect. Well, what does it mean that it's not perfect? It means it has some isolated points. So let's just throw out the isolated points. Okay? So we do that. So let's do that on the other board. So for a closed set, actually you can just find this for any subset, but for a closed set A, define, and Cantor's notation was A prime. In fact, he calls it the derivative set, like a derivative of calculus. But it's the derivative, it's a derived set from A. So that's not a prime, that's just a bit of ink that was left on the board. A bit of a nasty coincidence. So define A prime to be equal to A with the set of all isolated points removed. Okay. And an easy proposition, which is something for you to verify in your own time. It follows that A prime is again closed. So we retain the property of being closed. Okay. So the obvious thing to do is to take A prime here. Okay. But guess what? Let's ignore accountability considerations. It actually will be uncountable if you start with an uncountable set, but we need to prove that. We've thrown away all isolated points, but we might get some new isolated points that weren't there before. So a simple example is if we've got our set A, and let's suppose somewhere else in A, so this is part of A, we've got like a single Cauchy sequence converging together with its limit point. Now, if you throw, this part is already perfect, but this is the whole of A here. This part's perfect, but this part's not. If you throw out the isolated points, well, all these points here are isolated, but the limit point obviously isn't. And once we've thrown away the isolated points, then this point now becomes isolated. So we need to throw away the isolated points again. And guess what? We might create more isolated points in doing so. So there's an iterative process. So we're going to define a sub 0 to be a sub n plus 1 to be a sub n with the isolated points thrown away. And okay, I'm not going to have any W's in this proof, so let's go to omega. So an a sub omega would be the intersection over n of a sub n. But guess what happens? This isn't going to work. As it turns out, this might still have some isolated points. Okay? So guess what we do?
Go to Hartog function.
Well, we don't need Hartog's function, but the spirit is right. And this is the other reason for using omega here. We go on in the ordinal. So minus a alpha plus 1 is the derivative of a alpha. And this can be a lambda for a limit ordinal. So this is the intersection over all alpha less than lambda at a sub alpha. And now, well, now I'm going to use infinity. I don't remember what the notation in the notes is, but I don't want to look it up. Because a infinity is not, we don't know what the ordinal is yet. I'm going to define a infinity to be the intersection over all ordinals of a sub alpha. And this works. And this argument, so it was Cantor that proved that the closed set contains a perfect subset. It was this argument that caused Cantor to invent the ordinals. Right, so the ordinals were created in order to make a particular mathematical argument go through. So let's prove that this works. I'm going to actually use slightly different notation from in the notes. And I hope I'm not going to get into a mess because of it. But I'm going to define F alpha to be the set of isolated points in A alpha. So those that we throw away when we go from A alpha to A alpha plus 1. So this is, you can view this as A alpha plus 1 with, sorry, the wrong way around. So it's those points that we threw away in going from A alpha to A alpha plus 1. So in other words, isolated points in F alpha.
There you go.
In A alpha. Thank you. And I mean, some obvious properties of this are that A alpha is always closed because the derivative preserved being closed and an intersection of closed sets is closed. So this is Weidmann's finite induction. And also that if alpha is less than or equal to beta, then A alpha is the superset of A beta. Again, Weidmann's finite induction. So it's here we've thrown out some points and we're intersecting, so we're always making things smaller. And then if we look at all the points we throw out, so this is F is the union over all ordinals. So we've, a class of things of the F sub alphas. And in fact, this is a disjoint union because obviously at each alpha, we're throwing out elements that are still in the set A alpha. And then when we get to a greater alpha, those elements won't be there anymore to throw out. So we can't we can't throw an element out twice. Okay, so now we get the crucial argument, which is F is a countable set. So how do we see this? Well, each time we throw out an element, it's isolated. So we can find an interval that contains whose intersection with that contains the element, but whose intersection with that element is just that element. And we can write that as a function. So to see this, consider a function. Maybe I should check in the notes what I'm calling it. Okay, just F. So this is from all the elements we throw out to I, which is this. So I is going to be the set of P, Q, pairs of rational numbers such that P is less than Q. Okay. And F maps a Y in F alpha gets mapped to some interval Py, Qy such that Py, Qy intersect A alpha is distinct to Y. So what this means is we found a rational open interval. I mean, it's isolated, so there exists some open interval containing Y that doesn't contain anything else in A alpha. Because there exists some open interval, there's clearly a rational one. You just make the rational numbers, just find rational numbers just a bit smaller than your bound of your interval. And so we find some rational interval that indeed contains Y, but doesn't contain any other elements they are, because Y is isolated. Okay. Now, here we're making a choice, but we don't need the axiom of choice for this. Why not? Well, I'll take it. Okay. Why not? Because this is a countable set. There's pairs of rationals with one below the other. So we can enumerate it in a standard order. And we simply map any Y to the first interval satisfying this condition that we get in the enumeration. That gives us a rule for mapping Y to a chosen interval. Okay, so we don't need the axiom of choice. The other thing is this function is injective. And the reason for that is, suppose we consider, I won't write down the argument in full, but it's actually easy to see. Because suppose we consider two elements, Y and Y prime, and we consider where they're mapped to. So Y will belong to some F alpha, and Y prime will belong to some F beta. And one of alpha and beta will be less than or equal to the other. They might assume that we get Y first, Y prime second. But then, when we consider the first one, Y was isolated in A sub alpha, which contains also Y prime at that point, because we haven't yet thrown Y prime away. And therefore, Y prime is not contained in here, because Y prime is in A sub alpha, but Y prime is not in this intersection. So Y prime is not in this interval, so Y prime must be mapped within. Okay? This is injective. So because of this, we've got an injection from F into a countable set. hence F is countable. There's a full argument in the notes, but I think it's easier to see just in the template. Okay, so F is countable. So what does that mean? Well, so I guess I'll go up here. So F is a disjoint union of the F sub alphas. And because F is countable, there must exist some countable ordinal at which F sub alpha becomes empty. Otherwise, we would have a disjoint union indexed by the uncountably many set of all countable ordinals of non-empty sets, and that would be an uncountable set. So let me write it in just to emphasize what the argument is. So if for all alpha less than omega 1, so for every countable ordinal F alpha were non-empty, then F, which is the union over the disjoint union of, sorry, so this would be, we would have the disjoint union over the alphas less than omega 1 of F alpha, which is a subset of F, so this would be uncountable. Uncountable. Since we've seen that F is countable, so therefore there exists a countable ordinal, so that's an ordinal less than omega 1, such that F of gamma is empty. And let gamma be the smallest such countable ordinal by the least ordinal property. So henceforth let gamma be the smallest such. So what does it mean that F gamma is non-empty? Well, then we have A gamma prime equals A gamma. There are no, in other words, A gamma has no isolated points. And because this is A gamma plus 1, it still has no isolated points. And then the whole construction never again get, we just stay. So then for all beta greater than or equal to gamma, F beta is just F gamma. Sorry, not F beta, but, well, it is the empty set, but A beta is A gamma. So basically, we've stabilized, and so in other words, our A infinity, so A infinity is A gamma. We've seen it is closed because every A gamma is closed. We've seen it has no isolated points because of this. So of course, this is going to be our perfect subset. Why is it non-empty? Exactly. We started with an uncountable set and we removed the countable subset. Okay. So therefore, notice we only need uncountability for this argument. We don't need it to be continuum. So this is the power of the argument. It takes us from an assumption just of uncountability to a strong property, the existence of a perfect subset. And that's a strong property because the perfect subset, we know by the previous theorem, is actually has cardinality the continuum. So it has no isolated points and is non-empty. I mean, it's not just non-empty, it's uncountable, but of course we actually know because it's perfect, it has cardinality in the continuum, but it's non-empty because A, the initial set A is uncountable. Countable, so A with the countable set taken away is is also uncountable. But anyway, it's non-empty. Anyway, these 3 points together say it's perfect. And we're done. Jolly good. And I can't quite see. Oh, right. Well, it's basically 4 o'clock, so we'll have the break until the usual break until 1:15. Right. So as I said at the beginning, the goal today is to look at well-behaved subsets of real numbers and prove properties like that they really are. The well-behaved subsets really are well-behaved. So in this case, we looked at closed sets, and it was quite a deep result, even for closed sets, but we did manage to show that a closed set cannot violate the continuum hypothesis. So if it's uncountable, it is necessarily of continuum cardinality. And in doing so, we established this other property which is of interest in its own right, which is that any closed set contains, any uncountable closed set contains a perfect subset. And before closed sets, we looked at open sets, and they were even easier to think about because it's easy to classify what open sets look like. But obviously, there are many subsets that are not open or closed. So what can we say about richer classes of subsets? And what we want to do, I mean, what the direction I want to go in is looking at classes of subset that go beyond open and closed set, but are nonetheless, in a sense, well behaved. And this is the subject of, well, this is the topic of a subject of mathematics called descriptive set theory. It's kind of classifying well-behaved classes of subset of well-behaved subsets of Polish space. And at the moment, we've looked at the open set. And what descriptive set theories do is they start with the open sets and the closed sets as very basic kinds of sets. They consider other sets you can obtain from open sets and closed sets by reasonable combinations of operations. And the initial part of this subject, which is all we'll do in this course, concerns something called the Borel hierarchy. And we're going to define families of subsets of the Polish space. So we're going to have a sigma hierarchy and a pi hierarchy. So this is a capital sigma and a capital pi. And they're indexed by the 0 as a superscript. And this is not going to change. So one increases this to 1, you go into something called the projective hierarchy, which is something beyond the Borel hierarchy. But we're going to stay with 0. We have an index down at the bottom. This does change. And as you can see from the notation alpha, it's an ordinal index. So it's going to be an ordinal indexed hierarchy. And moreover, in textbooks, the capital sigma here is written in bold. So it's hard to do a bold on the board. So maybe one could underline it or something like this. So this is called the bold space hierarchy. And there is also a light face hierarchy, which is analogous, but is to do with computability theory rather than, we're going to connect more with topology rather than with computability theory. Okay, so I'm going to introduce you to this hierarchy, but to keep the notation manageable for the board, I'm just going to write sigma alpha with no zero and no underlining and pi sub alpha. And the pointer is we start with so alpha is an ordinal, and also alpha is greater than or equal to 1. So you don't have, there is no sigma 0 and no pi. I mean, there might be, but I don't know what they are. Yeah, anyway, people typically start with 1 here. So I'm going to tell you how we get these. So we're starting with 1, so let's start with 1. So sigma 1 is, so we've got a Polish space X. So I will actually define these for an arbitrary Polish space X. But if you're uncomfortable thinking about Polish spaces, just think of X as the real numbers. It's okay. I mean, the main content is that we're concerned with this week is for the real number. Okay, so sigma 1 is just defined to be the, I'd use this notation, then it's just a collection of open sets. So a set of open sets, open subsets. And pi 1 is, well, I don't know why, but in the notes I've got clearly A of X, and this is the set of closed subsets. I've written this rather big because we need to do more interesting steps, but hopefully I can bring things on board. So now it's ordinal index. Now, unsurprisingly, there's going to be a successor case. We're defining by, so these are defined by transfinite recursion. And they're mutually defined in that, to define sigma alpha plus 1, we're actually going to refer to pi alpha. And to define pi alpha plus 1, we're going to refer to sigma alpha. The sigma of alpha plus 1 is obtained by closing pi of alpha under countable union. So the idea of these families of sets here is the sigma families of sets, or all the families of sets are going to be closed under finite intersections and finite unions. So you have if you're in sigma sub alpha, you've got 2 sets in sigma sub alpha. If you intersect 2 sets, you're again in sigma sub alpha, and if you union 2 sets, you're again in sigma sub alpha. But in general, the sigma ones are going to be closed under countable unions, and the pi ones are going to be closed under countable intersections. Of course, open sets are closed even under arbitrary unions, not just countable ones. But in general, we're going to just ask for closure under countable unions, sigmas and countable intersections. So sigma alpha plus 1 is the set of all countable unions of sets in pi of alpha. Pi of alpha plus 1 is the set of all countable intersections of sets in sigmas. So let's actually write this one of these out as a formula, and you can easily make the other one a formula. So sigma alpha plus 1 is all sets of the form countable union, so union indexed by the natural numbers of A sub n, where every n in the natural numbers, A sub n belongs to pi sub alpha. Okay. So of course, the first case we're interested in here is sigma of 2, sigma sub 2. So sigma sub 2 is the collection of all countable unions of closed sets. We don't want to consider arbitrary unions of closed sets because every singleton is closed and an arbitrary unions of closed sets would just be all subsets. So we wouldn't be placing any restriction on the subset. The countable unions gives us a well-behaved family of sets. And in fact, I don't know if you do this in topology, but countable unions of closed sets have a name. They're called the F sigma set. Sigma 2 is the F sigma sets. But they say it's sigma 2 is F little sigma sets, and pi 2 is what I call G delta sets. In case you've met that before. Okay, so we close. The sigmas close the lower, the pi's below them under countable unions, and pi's close the sigmas below them under countable intersections. We get to limit ordinal. Well, it's not just the union, because the union wouldn't be closed under just.
Or is sigma 2 is Q sigma 2 if the anomaly singleton?
The sigma sub 2 is.
2 is Q an example. The rational.
Oh, okay. So yeah, the set of rational numbers is an element of sigma 2. Yeah, good. And so any countable set is an element of sigma sub 2.
Then for I call R minus Q reals without.
No. So pi 2 is sigma 2 is the set of all. It's a family of sets. It's a family of subsets. So Q is an element of sigma 2. And the set of irrationals is an element of pi 2. But there'll be, there are lots of other. In fact, so sigma 2 is countable unions of closed set. Every open set can also be obtained as a countable union of closed set. That's an interesting exercise, not very interesting, but anyway, simple exercise. So sigma 2 contains the open set. It also contains the closed set, and it also contains sets like the rationals. Okay, but it's a family of sets. Sigma sub lambda for a limit ordinal. If we just took the union of the sigma sub alpha for alpha less than lambda, it would not be closed under countable union. We need to make sure it is closed under countable union. So one way of doing that is it's the union of n of a n's, where for every n in n, a n is a member of some pi alpha sub n or some alpha sub n less than lambda. Okay, so we're taking countable union of pi sets from lower down the hierarchy. And pi sub lambda is the same, but this intersection, so again we replace this with sigma. Okay. And that's the definition. It takes a little bit of getting your head around, but anyway, works. And following lemma summarizes the main properties. And I've written them in the order in which one proves them. They're all proved by transfinite induction. And let's just write them as bullet points. And I need to remind myself, well, what they are and what the order is. Of their numbers, so let's number them. So firstly, as you go up the hierarchy, you have this alternation of these properties are obvious because pi is countable unions. A set is in pi if it's a countable union of sets in sigma. So if you take a single set in sigma alpha, then you can union it with itself countably many times and you get it back. So it's you clearly get these inclusions are obvious from the definitions. So more interestingly, we have that if alpha is less than equal to beta, then sigma alpha is a subset of sigma. Every sigma alpha set for a smaller alpha is also a sigma beta set for a larger beta. And also every pi alpha set for a smaller alpha is also a pi beta set for a larger beta. And there's a special case of this, is the claim I made earlier that every open set is a countable union of closed sets, because that's the inclusion sigma 1 is a subset of sigma 2. Okay. So thirdly, the sigma alpha is closed under, every sigma alpha is closed under countable unions. That's that. So this is again pretty easy from the definition and finite intersections. And pi alpha is, you just make the unions finite and the intersections countable. So fourthly, we have the duality between sigma sets and pi sets at the same level. So just like open sets are complements of closed sets are exactly the complements of closed sets and vice versa, sigma alpha sets are exactly the complements of pi alpha sets. So if B is a set in sigma alpha, then that holds for, so a subset of a Polish space X is a sigma alpha set if and only if X would be removed, the complement is a pi alpha set. And lastly, the important one, well, they're all important, but this is particularly important. So maybe to see this, let's draw a picture that we're starting off with the collection of all open sets and the collection of all closed sets. And we're defining now this collection of countable unions of closed sets. And by properties 1 and 2, we have that inclusion and this inclusion. And so let's actually draw these as lines so as not to get too messy. So kind of inclusions are following lines going up. And let's make this pi 2. So this, we have inclusions like this. And this picture repeats itself. So sigma 3, pi 3. So it just always looks like this. Sigma 4, pi 4. Anyway, we could go here, and then we get sigma omega and pi omega. And again, sigma omega plus 1, pi omega plus 1. And the ordinals are really a bit needed here because these inclusions are all the inclusions that I've drawn on the border strip. Okay? So we get new sets. By closing the pi sets under countable unions, we get new sets that we didn't have before. And by closing the sigma sets and the countable intersections, we get new sets that we didn't have before. But at some point, we obviously have to stop. And that point is at, well, not obviously, but you do. Otherwise, you would be embedding the ordinals in the set, subset. So it is obvious that you have to stop. And the point at which you stop is omega 1, the ordinal omega 1. So this is the last point, that sigma omega 1 actually equals pi omega 1, which equals sigma omega 1 plus 1, which equals pi omega 1 plus 1. And once you've got that information, you can see that this equals sigma beta equals pi beta for all beta greater than equal to omega 1. Okay.
You have exclusions split all the way up the hill. There are some uncountable Polish space because Polish spaces is good. Maybe.
Yeah, so indeed the countable spaces are, so if you start off with a countable space, then in fact, as soon as you get to sigma 1, you've got the whole power set, and pi 1 is the whole power set as well, and so everything is just the whole power set. So indeed, when I said these are strict, I'm assuming an uncountable space. A good point. Yes, thank you. You have the inclusion, everything here is valid for an arbitrary Polish space, but a strictness property is true only for a countable Polish space. So an uncountable Polish space. So in the case of an uncountable Polish space, omega 1 is the least ordinal with that property. And that is very hard to show because that involves showing that you get new examples at all countable ordinals. That requires quite some involved. No, we're not going to do that. But anyway, good point. Yeah, the strictness requires uncountable Polish space. Right. So maybe I'll leave in the notes. There's a proof of statement 5 here, but maybe I'll leave that for the lecture. It's not that exciting. The idea is you simply look at, well, we want to show that, for example, that sigma omega is omega 1 is a subset of pi omega 1. Everything in sigma omega 1 is a union of pi sets for a set of countable ordinals. But then you can just take the supremum of those countable ordinals, which is again a countable ordinal, and so by the monotonicity property, all the sets you're unioning will then belong to the same pi set for that supremum countable ordinal, and then they'll be in the, if you take that, if you call that supremum countable ordinal gamma, they're all in pi gamma, and so the union is in sigma gamma plus 1. Oh, hang on, we were trying to show, and hence in pi of gamma plus 2. Oh, well, actually, they're all in, yeah, the intersection was in, sorry, union in pi of gamma plus 2. Anyway, I don't want to get into the details of that. So this is the what's called the Borel hierarchy. And by this property here, we have the point you get to omega 1. You have a sigma equals the pi's, and so you get a collection of sets that contains the open sets, because that's what you started with. It's a sigma, so it's closed under countable unions. It's a pi, it's closed under countable intersections. And by this property, it's also closed under complements. Okay. And in fact, by transfinite induction, one proves so let me just, by property 5, the set sigma omega 1 is closed. So, but in fact, well, using, it's not just all the properties, but by this lemma, sigma omega contains every open set. Because it contains, sorry, sigma omega 1, because it contains sigma 1, and is closed under countable union countable intersection and complement. So hands up if you met the Borel sets in a mathematical subject. Okay, so you may know then the Borel sets subset B. So this is the collection of all Borel subsets of a Polish space. But if you're not happy with Polish spaces, think of it as the reals. Is defined to be the smallest collection of subsets of X closed that contains the open sets containing all opens and closed under countable unions, intersections, and complements. And actually, if you have countable unions and complements, then you don't need countable intersections, because you can derive, or it's enough to take one of countable unions and countable intersections, if you've got complements. So closed under, but anyway, let's put them all down: countable unions, intersection, and and a straightforward theorem that B is the same as sigma omega 1. The proof here, well, sigma omega 1 is contains every open set, is closed under countable unions, intersections, and complements. B is the smallest family of sets with that property, so B is clearly a subset of sigma omega 1. So by the so this is by the definition of B. And the other direction is you prove by transfinite induction, and it's straightforward once you've got the properties of the lemma, you prove by transfinite induction that for every alpha, sigma alpha is contained in the set of Borel sets. They prove for all alpha, sigma alpha, subset of Borel sets B by transfinite induction. So basically, what we've done is we've obtained the Borel set in this stratified way. We've got this stratification, this hierarchy that takes us to the Borel set. This is why it's called the Borel hierarchy. It gives us a nice handle on the complexity, if you like, the descriptive complexity of a Borel set. How many times, in order to get a Borel set, how many times do you actually, you start off with just opens and closed set, how many, in a transfinite way, operations of countable union, countable intersection, and countable intersection do you need to apply in order to get the Borel at the bottom of consideration? And that gives you an alpha that places it somewhere in this hierarchy. Okay, so we get a nice understanding of the Borel sets here. So I want to just end with two properties of Borel set. So the first is, this is another, the Borel sets are another class of well-behaved subset of the reals. And it turns out that, again, Borel sets can't violate the continuum hypothesis. So again, we have a collection of Borel sets enjoy the perfect subset property. And I won't write down what that means again, but what it means, I'll just say that what it means is every uncountable Borel set has a perfect subset. Now this is not terribly hard to prove. but still, we proved it for closed sets today. That was enough work, I think for today in terms of this kind of proof. So it's quite a bit harder than the proof for closed sets, but still, it's it's a nice property, and it's again establishing that Borel sets, even though they're much richer than closed sets, Borel sets nonetheless enjoy this property that you got an uncountable one, it has a perfect subset. Okay. And I just want to end with something else. Could it be the case that actually the Borel sets are all subsets of the real numbers? We're doing this big construction of the family of Borel sets. Maybe actually we can establish the continuum hypothesis, although you should know by now that we're not going to be able to. But it might be plausible on first sight that you could establish the continuum hypothesis we've proved, well, we haven't, but people have proved that Borel sets enjoy the perfect subset property. Maybe we could just prove that the Borel sets are all the subsets of the real numbers. But that's not the case. So does anyone know why that's not the case? Some of you have studied. So this is going to be the last theorem today. So how many Borel sets are there? Sorry? What did you say?
41.
2 to the other zero. The theorem, cardinality of the family of Borel sets is 2 to the other 0, whereas, so now let's just think about the reals. So we'll compare CF dot, the common abbreviation for compare with, the cardinality of the power set of the reals is what? 2 to the other step. So strictly. Okay. So I want to briefly prove this theorem that we can't. So this is something that. So a few of you said you've done Borel sets. Is that in a probability theory course or in topology or in measure theory? Okay, measure theory. I mean, maybe they stated this, but they wouldn't have proved it because you can't prove it, and you can't prove it without well, maybe you can, but anyway, the natural way of proving it is by transfinite induction. And in order to prove that, you need the Borel hierarchy. And once you've got the Borel hierarchy, we can prove this because what we prove by transfinite induction that for all alpha, the cardinality of sigma sub alpha is less than equal to 2. Yeah, well, equals, but we'll prove that it's less or equal to 2 to the other 0. It's obviously not strictly less than, because already at sigma 0 there are 2 to the other 0 many open sets. So that's really easy to see. But it's trivial that there are 2 to the other 0 many closed sets, because every singleton is a closed set. But anyway, we're only going to worry about this less than or equal to half. So the proof is by transfinite induction. Sorry? So this will work for any uncountable Polish space, but we'll deal with the case. We'll deal with the case. But I should say that in this proof we actually need the real AC. So this is the only part of today's lecture that we need AC. So we want to prove by transfinite induction. Yes.
You said we want to see the continuum hypothesis. But here in the proof, while checking if we can make some prediction, you use AC, but with that can't be do the hypothesis. So what's the point of the proof we use?
So I don't understand the question, but so AC is the axiom of choice. Then so not the continuum hypothesis. But anyway, I didn't quite understand the question, but I don't want to overrun because it is also a holiday week to rest. So in the notes, there's the step case and the step case and the case for a limit ordinal. The case for a limit ordinal is a bit more complicated, but still the idea behind it is basically the same as in the step case. And so because there's limited time, let's just do the step case. So the step case is, and we'll also, maybe we'll put in as an induction hypothesis for proving both case for both sigma and pi. So for the step case, let's just do sigma alpha. For the step case, we're going to prove that sigma alpha plus 1 has cardinality less than or equal to 2 to the L 0. So I think I need my notes for this. So I don't get to a wrong. Aha, right. Yeah, so we notice. So we're looking at alpha plus 1. So we notice we have a surjection from pi alpha functions from natural numbers to pi alpha set to sigma alpha plus 1, which is countable intersection. And so this surjection gives us that the cardinality of sigma alpha plus 1 is less than equal to the cardinality of pi alpha to the n. Because using the axiom of choice, this is a surjection. We can find a section for the surjection that maps every element here to a particular sequence whose intersection is that element. Okay? So here we're using AC. Well, and then this is less than equal to, by the induction hypothesis, 2 to the aleph 0 to the aleph. So that's the pi alpha part to the aleph 0, and that is, of course, 2 to the aleph 0. Okay, so the step case was really easy. The limit case is just like a slightly more complicated argument based on a similar idea, but notice how we really did need the axiom of choice in getting this inequality there. Okay, so I think I probably could do the limit case too, but I think that's enough. Are there any questions? For example, your question particularly. Yeah, okay. Maybe I said the wrong thing as well. That's always very possible. Any questions? So if not, I wish you all a nice holiday weekend. And yeah, and before next week, try to think about the Polish space of infinite functions from natural numbers, which I defined at the beginning of the lecture.